Welcome everyone to Mr. Physics World Radio Voice. I'll be working out number 14 for you today. The page is 342. Actually, I'm going to modify it a little bit, but here's the setup.
Where's your voice?
Quiet on the set. People these days. Okay. What we're finding out first is what is the period and frequency of the motion. So the first thing that we're thinking here is to find the period, we have a new formula that tells us that that period depends on the mass of this and the spring constant. I know both of those things. So I should just be able to put this in. Mass is 0.75 kilograms, spring constant 124 newtons per meter. I get that times by 6.28-ish for 2 pi. I'm getting 0.49 seconds, so about a half a second. Then I remember that frequency is how frequently something's happening, how many cycles per second. So that's 1 divided by the time it takes for a complete cycle. So 1 over 0.49 seconds, and we're getting just about 2 cycles per second, which is the same as hertz. So there is part A. Okay, part B then says, what is the amplitude? Now your book will give you a bunch of math with sines and cosines that you can figure out. If you care to go back and do that, you can. I think there's an easier way. The easier way is to do it with energy. And just like that problem on the worksheet said, that the maximum kinetic has to be equal to the maximum potential, basically, which means 1/2 mv squared must equal 1/2 kx squared. But there's one difference in this problem. The difference is this was given a push to begin with. It didn't start off at rest. So that means it's like at equilibrium, the block is, and then we smack it and get it moving. So at time 0, it's moving, which is a little bit different than the other case. So that means that I should be able to, this thing is starting at the equilibrium point, basically. So if that's the equilibrium point, it's starting there with its kinetic energy. So 1/2 of 0.75 kilograms times the velocity of 2.76 meters a second at the beginning equals 1/2 k, and x is what I don't know, and x in this case is the maximum displacement, which is the same as the amplitude. Call it x or k, it doesn't matter. The 1/2 should cancel on both sides, so I can kind of forget about that. So if I go 0.75 times 2.76 squared, then I divide it by 124, and then I take the square root of that. That then gives me the amplitude. So I'm kind of skipping some of the algebra. You can work that out if you like. And that would be meters. So 21 centimeters is the amplitude, which means that this thing goes 21 centimeters before it hits the turning point for that problem. Part C, what is the maximum acceleration? This is the part that people usually freak out on and don't know how to find. But remember, the acceleration can be found with Newton's second law. And Newton's second law, the force here is the stretching force, kx, negative because it's always in the opposite direction, or almost always. The maximum is at the farthest stretch, and that's the amplitude. So this is negative 124 newtons per meter. This is 0.21. That's the amplitude or the maximum stretch. And then the mass is 0.75 kilograms. So we're 34.7 to, this should be acceleration, so it should be meters per second squared. It's negative because it's fighting the direction you're going. And this is happening, remember, right at the turning point. So when this thing is out here and it's hit the end of the spring and now it's stopped for a split second coming back, that's the maximum acceleration. Just like the maximum for the bungee cord jumper was when it was farthest away from the bridge, stretched the most. Okay, D is the part I'm going to change up because we're not going to deal with D on this one until next class. What have I got? 3 minutes? Something like that? Let's find kinetic energy at 1/2 the amplitude. So that means 1/2 the amplitude would be 1/2 of 0.21, which is 0.105, 10.5 centimeters. So what's the kinetic energy when I'm at that point right there? I can solve that with energy because I know the maximum kinetic energy. I found that already. And then the energy at that point is when I'm halfway, that means I'm right here. I have some kinetic and I have some potential. And so this is 1/2, 0.75 kilograms times the maximum velocity. And then this is what I'm trying to find, the kinetic energy. So I actually could just leave that as a variable, just finding Ke. And then the potential energy at that point is 1/2 K, 124. And the X now is at 0.105, so I'm 10.5 centimeters past equilibrium. So I've got some stored potential, and that has to be squared. And now I should be able to find this, subtract that amount, and get the kinetic. That sound is annoying. 1/2. So that many joules, then I've got to subtract all this stuff. Which is 0.68. All of this is 0.68, so I'm subtracting it. So what is that, 2.18 or something like that? Yeah, 2.18. So there's 2.18 joules of kinetic. Had they asked me to, I could have found what the velocity was, but they didn't ask that. Part E is what's the total energy. This part will do the same. We've already figured that out. It's either when it's all kinetic or when it's all potential. And since we know the kinetic is 2.86, no need to find anything else out. That's the total energy. And that's a wrap, people.